Hello friends, today I'm going to talk about special relativity. So there are two rules in special relativity. One is that the speed of light is constant at a vacuum. It will be the same for every observer, 300 million kilometers per second. And the second postulate is that, for example, if you're going in a plane or spaceship which is going at 900 kilometers per hour for example, then there's no way that you can realize that you are moving, and you need something to relate to or compare to see that you are moving. And this is that means the reference frames are impossible to distinguish. Now here's a whole bunch of examples for that. One is, let's imagine there's Earth and there's a person who's standing on this Earth, and it's a spaceship, and the spaceship is driving by one person. And this spaceship is also going at the speed of light, the maximum constant of the universe. And then when this zooms by, there's a mirror which will follow it. From the person who's in the spaceship, it will seem that the laser will go straight up and down by the mirror. It gets reflected. But from the person who's at Earth, it will actually form a V shape. Here's why. Because when the spaceship starts here and it releases the laser, then it will hit it. But it will hit it diagonally. But then when it comes, again, when it's reflected, this spaceship goes even more farther, and then it will receive it, causing a V shape. Now let's imagine that there are three spaceships. For example, here, here and here. And the center spaceship will release two lasers, which will then there is the two other spaceships in the left and right has a laser receiver, and the center one will release two lasers. From the person who's shooting that laser, it will seem that both the lasers for the spaceships will receive at the same time. But for the person who's at Earth, it will seem that the left spaceship will receive the laser first and then the right spaceship. Now let's have another example. Let's imagine the three spaceships again, but instead of lasers, the center one releases a command to fire the engines at once. From the person who is releasing that command, it will seem that all the spaceships release their engines at once, and the distance between them remains the same. But from the person who's in Earth, it will seem that the left spaceship will come closer to the middle spaceship, then the middle spaceship will release the exhaust, and then the right spaceship, one by one. And this means that the distance will get shrinked. Now let's see how we can link magnets to special relativity. So examples like iron are a magnet, a permanent magnet. That means they can attract to a magnet. But copper, for example, doesn't attract to a magnet. But if you have any material in an electromagnet, it will become a magnet, a permanent magnet. But now let's see how we can link this to special relativity. Let's imagine a copper tube where there's protons and there's a sea of electrons flowing around them. Because there's an equal amount of protons and electrons, they organize. The top one will become all protons and the bottom will become all negative ions. And now let's imagine there's a ball which is fully made about positive ions. Then even if the negative ion flow is moving, then the ball will not have any repulsive field. Okay, it will not have any repulsive force. But if the ball is moving, then it will feel a repulsive force. And this is why. Because then the negative ions will get much farther apart in density, and the protons will get much squished up, and then it become a higher density, and then because of this the ball is repelled. But from our perspective, the ball is pushed because of a magnetic field. So this is how we can link magnets to special relativity, and this is special relativity. Thank you.